First, a couple of announcements. If you are with us today for the first time, we weren't here yesterday, get the syllabi. Oops. Anybody need the syllabus? Come get right now if you need it. Lab classes now should be all checked in. So 46L should be flying along. Now, a definite problem of 46L starting the first day of class. It'll be a couple of days before in class we have the opportunity to be discussing the stuff which you are investigating by experiment in 46L. But I hope by now you've recognized, at least those of you who are with us in 45L, that I've tried hard to write the laboratory manuals to support your understanding of what goes on in the laboratory, whether or not you hear about it in lecture. So if you pay attention to what's in the lab book, you should be fine and you should be able to understand and appreciate the intent of the work that you do in lab. Be that as it may, we will be tackling that stuff in a couple of days in lecture in detail. Also, you've looked in the syllabus, I trust by now, and seen that there will be material from 46 Laboratory for which you shall be responsible in this gathering. But in order to protect those of you who are not in 46L, anything from 46L for which you're responsible in this gathering, I will discuss in detail in class. So you won't be shortchanged. You won't be disenfranchised. I also announced yesterday that there is insufficient enrollment to maintain 2 discussion sections for Thursday period 1 as well as 2 discussion sections for Thursday period 2. So all the people who are registered for period 1 will meet in one room. I'll decide later today on the room. Be Leaf 142 or 242 or something like that. Same for period 2. For period 3, there are presently 3 discussion sections on the books. One of those discussion sections is going to disappear. Those who are in that discussion section will not go to a different period. You will just go to a different room at the same time slot. I'll announce which room and which students are involved tomorrow. Now, for CLC stuff, I had hoped to be able to, by now, have a CLC schedule ready to go. But this morning, the chemistry email system was fouled up. For unusual reasons of which I know not at all, I could receive messages, but I couldn't send messages. That was finally fixed about 30 minutes ago. That hardly gave me enough time to take care of this issue. So I expect to have a CLC scheduled ready to go by tomorrow, and as soon as I've got a CLC scheduled ready to go, not only will I announce such here in class, it will be also posted on our Sockeye class information website. Now, another reminder. In our syllabus, on page 2, the second side of the syllabus, near the top, you'll see a short paragraph which starts with the caption, Horvath's request. I ask, please, that under no circumstances, for no reason whatsoever, immediately before class, when I'm in here scrawling stuff on the board, that you approach me at that time with any question or consideration. Because I try to come in here with my mind freshly packed with the information in organized fashion that I intend to discuss with you folks that day. And if you come in and throw me some kind of curveball that I'm not prepared to answer at that time, I may well get scrambled up. I assure you, I'm no magic man. I assure you that many of you have far more natural raw intelligence than I have. The upper hand that I have is I've been at this game for going on 45 years. And you have hardly had that much time. In fact, I doubt that any of you have been here for 45 years. In fact, I doubt that any of you have been here for any time which even approaches 45 years. But guess what? I don't want you to have to spend the many, many years which I have had to spend sifting through all the chemistry that's out there, so to speak, to distill it into what I now consider gets at the very heart and soul of the stuff which we shall discuss with you this term. So my plan is, when you go away from this gathering in 6 weeks, you will have the benefit of all these years of hard work on my part. I don't want you to have to spend all that time and all those years and lose all that sweat to be able to come up with the information and its understanding that I intend to share with you. My intention is simple. Difficult to achieve, but the intention is simple. I wish to share with you everything that I know about chemistry. Now, I know that's not possible, but I guarantee that's my aim. I hold nothing back. Anything which I understand, I believe you're capable of understanding, so long as I do the presentation properly. So what's your obligation in this game? Well, as I told you, you have to be with us all the time. Because this course and the material upon which you shall be tested is defined by what we do in class, nothing else. What we do in class tells you where we are and it tells you what we're doing. That's why you got to be here with us. I already said that. But it's important, so I just said it again. I think that's all the announcements. Let me take a look. Yep. So here we go. I trust by now you all have the chem notes, because without that, you're already without any chance whatsoever to be successful. You will see how the in-class presentations parallel what's in this note package. The advantage you have is now you can pay attention to our attempt to explain this stuff so that you can understand it and appreciate it, as opposed to spending your time trying to write down all the notes. But you don't got the notes. You don't have to write them down. Chemical equilibrium, chapter 17. We introduced you in brief to this consideration tomorrow, reminded you that this is extremely important because, practically speaking, all reactions under appropriate conditions achieve this condition. It's a dynamic condition. In an equilibrium system, reaction is taking place which converts reactants to products, while at the same time and at the same rate, a counter reaction is taking place which converts products to reactants. But since the rates of these opposing reactions are equal, when a system is at equilibrium, it matters not how long it stands, there will be no change in composition of the system whatsoever. And we have to learn about this system. We have to understand not only the system, we have to learn how to control it. Because, in the main, what our task is as students of chemistry when it comes to equilibrium is to learn how to outfox equilibrium. And in order to outfox equilibrium, we have to first understand it. Then we can learn how to outfox it. So let's get at the understanding part. First comment, my apologies for having made a goof on the very first page of chapter 17. Near the bottom of page 1, you'll see an equilibrium constant expression written for a hypothetical equilibrium reaction where hypothetical reactant A gets together with reactant B to make 2 moles of C. The typed equilibrium constant expression for this reaction is incorrect. It's inverted. So fix it. It's correctly written here on the board. This illustrates the difficulty that one runs into when one attempts to proofread his or her own stuff. Because your eyes keep seeing what you think is there. Because what you're seeing is with your mind, as opposed to seeing what really is there. You see what you think is there, and you miss this kind of stuff. Well, I've learned a lot since that time. And now before I submit anything to publication, I will have someone else who's knowledgeable about chemistry get out his or her red pen and proofread my stuff. And cut it to pieces to the extent that it deserves being cut to pieces. So I can fix it before I foist it upon you. So fix that. Now then, we had this on the board yesterday. We're considering 4 systems. 1 molar calcium chloride solution, 1 molar hydrochloric acid solution, saturated calcium carbonate solution, and 1 molar acetic acid solution. For those of you who were in 45L with us, I hope you remember you've had experience with each and every one of these systems. With each and every one of these systems, you've done some work. Do you remember the experiment, the assignment in which you did this work? Like assignment 4, which was the first real university level experiment which you folks did in 45 laboratory. Assignment 4. And one of the main intents of assignment 4 was to get you to understand something very important, which today's very wonderful, quote unquote, very expensive general chemistry textbooks have not yet realized. That's why I'm not letting them damn books in here. If you wish to do chemistry on a system, you better know what's in the system. And the components of a system don't talk to you. If you look at 1 molar hydrochloric acid solution, 1 molar calcium chloride solution, you're looking at a system that looks just like straight water. The fact that calcium chloride solution is loaded with calcium ions and chloride ions, the 1 molar. The fact that hydrochloric acid solution is loaded with hydronium ions and chloride ions, each at a molarity of 1. These things don't holler when you look at the solution. Calcium ion and your ion. No, it doesn't happen. So you as a student of chemistry have got to learn how to take a label on a bottle, like any of these 4 labels. And by understanding the chemistry that occurs when these systems were prepared, know what's in the system. Then you can understand the chemistry in which these systems may engage. But without that knowledge, you can't do this. And I haven't seen a textbook yet which tackles this. It's hard. It's difficult. So what have I referred to with this conversation? Do you remember the term we applied to this, we defined for this in Chemistry 2045? It came along in assignment 4. It's called Principal System Inventory, PSI. Because unless you can construct a principal system inventory, which is a list, a formula list of the main components of the system you are doing business with, investigating, you can't do anything with the system. Not from an understanding standpoint. Now then, back to the issue of equilibrium and these 4 systems. So, I'm going to regenerate the calcium chloride solution simply because after I made this solution yesterday, I forgot which flask had the solution. Yeah, they look alike. I don't know which one. So I threw out what we had yesterday and we'll start again. I got a nice big spatula full of calcium chloride. We'll have another nice big spatula full. Well, not quite full, but I'm trying to avoid making a mess. Calcium chloride generically is what kind of compound? Ionic, isn't it? How do you recognize calcium chloride to be ionic? By way of formula examination. You look at this formula, calcium chloride, and see immediately that this stuff is composed of ions derived from a metallic element and a non-metallic element? Well, but many compounds which have this characteristic are ionic, but many are not. So we put off the study of those which are not pretty much to the end of the first year of chemistry. Time permitting, at the end of this term, we'll talk about compounds of transition metals, which in many cases are notoriously covalent in character as opposed to being ionic in character. In any case, all the calcium chloride which I shoveled into this original batch of deionized water has dissolved. In this system, is there equilibrium existing right now involving solute? The solute was calcium chloride. Is there equilibrium in this system involving solute? Yes or no? Well, let's make another system to assist you in answering the question I just asked you about the first system, the calcium chloride system. This is reagent grade calcium carbonate. You familiar with calcium carbonate? Principal component of eggshells, many crustacean shells. Calcium carbonate particularly soluble in water. You ever cook eggs by hard boiling eggs? You see the shell dissolve? If you hard boil your eggs in acetic acid solution, you'll see the shells dissolve. I don't know that I'd want to eat the eggs then, but you'll see the shells dissolve. There's a lot of water in the ocean? Oh, a lot of water in the ocean. Calcium carbonate, the main ingredient of oyster shells. You see any embarrassed oysters because their shells have dissolved in all this water called the ocean? No, you haven't seen that yet, have you? That suggests that this ionic compound, calcium carbonate, among other things, shows one big difference in comparison to calcium chloride when it comes to water solubility. Here I've got some calcium carbonate collected on my spatula. Put a little bit more in. Calcium chloride solution. Or let's call it the calcium chloride water system. Calcium carbonate water system. Now the calcium carbonate, which I have shaken with the deionized water, is very tiny particle-sized calcium carbonate, powdery calcium carbonate. If we let this stand for a while, and it's already starting to happen, since calcium carbonate is more dense than water, you'll see eventually that the cloudy nature of this mixture will disappear as the solid settles to the bottom. I think you can begin to see that happening already. Now then, remember the question I asked you about the first system? Does equilibrium exist involving calcium chloride in this flask? Now I'll ask the same question, but about the second system. In the second system, does equilibrium exist involving calcium carbonate? Yes or no? Yes. We got a mixed bag of answers. We got yeses and nos. If equilibrium is to exist between a solid and a liquid solution, after dissolving some of the solid in preparing a solution of that solid, what observation must we make if we are going to conclude that equilibrium exists in the liquid-solid mixture that involves the solid? What observation do we have to make? You did this in 2045 laboratory. Now I expect you to put it to use. What observation do you have to make? Do you not have to see some undissolved solid? Do you see any undissolved solid here? $64 question. Watch out before you answer this. In this container, is there any calcium chloride? Is there calcium chloride in this container? Remember, calcium chloride is a white crystalline solid. I showed it to you. Is there any calcium chloride in this container?
No.
Not any. Is there calcium carbonate in this container?
Yeah.
Yeah. It's the white powdery solid that you see have settled to the bottom. So in this container, I have equilibrium involving solute. In this container, I do not. So, at the minimum, we see, as we already mentioned, calcium chloride is obviously a lot more soluble in water than is calcium carbonate. Now, that means for system A, the calcium chloride system, in preparing 1 molar calcium chloride solution, it follows that A, calcium chloride is pretty soluble because you would never get it to be able to dissolve to a molarity of 1. And this reaction is strictly a one-way street. What is this reaction? This is the reaction which shows the chemistry that occurs when the ionic compound calcium chloride is dissolved in solvent water. The AQ tags just tell us that the solvent is water. AQ for aqueous. You know this. And the name for this chemical process, is called dissociation. What does dissociation mean? As we go through this, we're going to use a lot of words and terms, and you have to know what these words and terms mean if you're going to understand the conversation. What's dissociation mean?
Splitting of an ionic into its respective ions.
What's dissociation mean? Separation. That's all. Calcium chloride is an ionic compound composed of the 2 ions, calcium ion cations and chloride ion anions, and these ions separate from each other as calcium chloride is dissolved in water. They separate from each other because the calcium chloride lattice is destroyed in this process. The water molecules with ion dipole interactions attack the chloride ions and the calcium ions on the external surface of the calcium chloride which I added to the water. And after the ion dipole forces outmuscle the ion-ion forces, they pull the calcium ions and the chloride ions into solution. All I've done is describe to you what happens when an ionic solid, in this case calcium chloride, is dissolved in water. And since it involves the coming apart of the calcium ions and the chloride ions from each other, as the calcium chloride lattice is destroyed by this process, it's called dissociation. Now then, since no calcium chloride remained after we prepared the 1 molar calcium chloride solution, there's no equilibrium involving solute. Now let's take a look at 1 molar HCl. I'm not going to prepare any 1 molar HCl solution for you because that would require me to use some hydrogen chloride gas, which is a rather noxious material, difficult to handle because it's a gas, and noxious and dangerous because of its chemical nature. But you're familiar with this chemistry. You did it in 45L. And I've written here the equation for the reaction which occurs when hydrogen chloride gas is dissolved in water liquid. This process has a different name as opposed to dissociation. Now, it is true that in this process HCl molecules come apart. But they do more than just come apart. What is it that these HCl molecules do besides just coming apart when I dissolve HCl in water, given that that's the equation for the reaction which occurs? What are these HCl molecules doing? Well, clearly, if you look at the equation for the reaction, as reactants we see molecules, don't we? And as products we see ions, charged particles. So we're turning molecules into ions. So beside dissociating, the HCl molecules are reacting with water molecules to create ions. That means, and you did stuff like this in 45 laboratory, if I were to liquefy hydrogen chloride and measure its conductivity, you think I'd get much conductivity exhibited by liquid hydrogen chloride, given that it's molecular? In 45 laboratory, you were asked to observe the conductivity of pure water. Our version of pure water in lab is deionized water. Did you get much conductivity from the sample of deionized water with the handheld conductivity meters? Did you get an on-scale reading at all for the deionized water with the conductivity meters? No. But do you know that deionized water does in fact have a measurable ion concentration? Have you heard about pH? I guarantee in a few more days you will have heard about pH. Wow, will you have heard about pH? Because in pure water, where the molarity of the pure water liquid itself is 55 moles per liter. Pardon me. 53 moles per liter. Or is it 55? 55 moles per liter. Okay. That in this pure water, you have a measurable ion concentration. 1 times 10 to minus 7 for the hydronium ion concentration, and 1 times 10 to minus 7 for the hydroxide ion concentration. Those concentrations are pretty daggone small compared to the molarity of water itself. Which means that in pure water, water molecules react with water molecules to make hydronium ions and hydroxide ions. That's an ionization reaction. But the extent of that ionization reaction is daggone small, as revealed to us by the fact that the conductivity of pure water is pretty daggone slight. But now let's talk about hydrochloric acid solution. From your work in 45 laboratory, what do you remember about the extent of this reaction in preparing 1 molar hydrochloric acid solution? What do you remember about the extent of this reaction? Extent. Put another way, if I go to the laboratory and I see a flask, stoppered, it's got a colorless liquid contained within, and a label on the bottle that says 1 cap MHCl. What's this label tell me? That label tells me that for every liter volume of this solution, with water being the solvent, for every liter volume of this solution which has been prepared, I dissolve 1 mole of HCl to the solute. That's what that label tells me. Label on the bottle. I call it M sub I, initial molarity. Does this label tell you what's in this solution? Does this label tell you what's in this solution? Yes or no? You did this in 45 lab. You think in 45 lab I was attempting to lay foundation for what we're talking about right now? You're damn right. Because this stuff is important, but it's also tough. Because in 1 molar HCl, that ionization reaction equation I wrote, HCl molecules plus water to make hydronium ion and chloride ion, extent EXT for extent, 100% in 1 molar HCl. 100%. So let's go back to this bottle, this flask which bears this label. Clearly this solution was prepared by combining HCl molecules with water molecules. But here's the $64 question. If I ask you to write a PSI, a principal system inventory, for 1 molar HCl, are you going to write this? Because that reaction went 100%. Are any of these molecules left in that system after the system was prepared? Not a damn one. So whenever I see a general chemistry textbook which prints this garbage on their pages, out it goes. And every one of them does this. You see why I won't let that junk in here? They lie to you, and I'm serious about this. It makes me mad as hell. Because you're the ones that are here to learn. And how in the hell can you learn when the book is telling you a bunch of fibs? Because they haven't paid attention to the chemistry which occurs when in a case like this, that system is prepared. You can't do chemistry like that. How would I verify that this reaction is going, at least to a large extent? What would I do in the laboratory to find out? You did this in 45, Lel. What would you do? Measure conductivity, because this is a reaction which converts molecules to ions, and it converts the molecules to the ions very effectively, does it not? It goes 100% when I make 1 molar HCl, which means that the HCl solution is damn conductive. In fact, if you recall your work in 45L, you couldn't get an on-scale conductivity reading for 1 molar HCl. You couldn't get an on-scale conductivity reading for 10th molar HCl. You couldn't get an on-scale conductivity reading for 100th molar HCl, because in each of those solutions the ion concentration is too damn great and gives you a total ion concentration which supports the conductivity that exceeds the capacity of our little inexpensive conductivity meters. You had to get that solution diluted down to about 1,000th molar before you could get on-scale readings. Any of you remember this from assignment 4 and 45L? Did you kind of remember? So then, for system A, our PSI is calcium ion, chloride ion, and what else? What's the main ingredient of any of these solutions? Water. Calcium ions, chloride ions, water. Now then, system B, the hydrochloric acid solution. Main ingredients: hydronium ion, chloride ion, water. Period. Any of these left? None. Zero. They all reacted. So if you write this down as a component of hydrochloric acid solution, 1 molar, on any of my quizzes or exams, I'm not going to just call it 0. I'm going to call it minus 100. Because you've written something which is horribly absurd. Because it doesn't fit with chemical fact. And I don't give a damn what these big expensive textbooks print on their pages. If they put that on the page, out the door that book goes. So, as we asked with this system, now let's ask you with this system. In this system, is there an equilibrium existing involving solute? Because the solute's HCl. No, because all the solute disappeared. Now, it is true. If I keep HCl solution with water being the solvent, if I keep that system closed, and I keep bubbling in HCl gas until I get the molarity up above 6, I can get some undissolved HCl. I can get some HCl-AQ in there. But the main components of that system will still be by far hydronium ions and chloride ions and water molecules, not HCl molecules. Now let's go back to system C. We have already investigated system C Here it is again. Now the calcium carbonate undissolved has settled to the bottom. I really didn't put much calcium carbonate in here. You see a white powder deposited at the bottom. So we know in System C that finally we've encountered a system which involves equilibrium involving solute. So we can recognize that since this is the reaction which occurs for System C, because this, like calcium chloride, is an ionic compound, is it not? But after this reaction proceeds and saturated calcium carbonate solution is developed, equilibrium is established. So I can write this for this reaction system. The first time I can write it for the systems we have so far investigated, where solute is involved in equilibrium in the system. So, for System C, I ask right now on your paper that you write the equilibrium constant expression for System C. Pretty easy. Do it. C what's the equilibrium constant expression? Now then, to repeat, an equilibrium constant expression contains exclusively solute species and gases if the system also contains gases. Nothing else. No pure liquids, no pure solids. Even though they may well be part of the equilibrium reaction itself, they're not included in the equilibrium constant expression. Because an equilibrium constant expression from a magnitude standpoint, a number value standpoint, depends exclusively on the components of the systems whose concentrations for solutes, partial pressures for gases, change as equilibrium is established. That's it. How many wrote this? How many wrote this and put calcium carbonate underneath? If you did that, that's wrong. Because we said equilibrium involving solute. Let's look back at the calcium carbonate containing flask. You see this calcium carbonate on the bottom? The calcium carbonate on the bottom. Is that solute? Is this calcium carbonate in solution? This isn't in solution. You think you're being in solution just by being in contact with water, like this calcium carbonate is? Believe me, if you were in solution, just as a consequence of being in contact with water, you'd take one shower, that's all. You'd go swimming once, that's it. And you'd dissolve. And down the drain in the shower you'd go. Or into the body proper of the Atlantic Ocean you'd go with the rest of the UF students who flock to Crescent Beach on weekends. I'm telling you what, when I was here as a graduate student, we didn't miss any weekends at Crescent Beach. From March, April, May, June, July, August, September, October. I'm telling you what, we were there with our beer and our sandwiches and our fishing poles and our swimming trunks, and we had a blast. With my 69 Chevelle, which is 300 horses under the hood, taking us there. Ha ha ha! I had a hell of a good time. And I still am. Now then, as a peek to the future, let's see if we can get this reaction to occur. I'm going to take this saturated calcium carbonate solution. Again, we know it's saturated because there's undissolved calcium carbonate at the bottom of the flask. I'm going to treat it with some of this indicator. Those of you who are up close, can you see the label on this bottle? It says HPHTH. Anybody remember what HPHTH is abbreviation for? What is it? Phenolphthalein. How many of you in high school chemistry, I know you did this at 45L, But how many of you in high school chemistry had experience with phenolphthalein? What'd you use it for? Did you use it as an acid-base indicator? Yeah. We're going to talk a lot about indicators when we get in chapter 18. Phenolphthalein is colorless. Is that clear? It's colorless. Is that clear? At a pH lower than 9. But about 9.2 it starts to change color. And if you get pHs substantially above 9, solutions which are becoming rather basic, then you see a red-pink color shown by phenolphthalein. Because the acid phenolphthalein molecule at pHs which are high, the acid phenolphthalein molecule loses H+. And this converts the phenolphthalein molecule to the phenolphthalein anion. I won't bother to try to name it. It's a large anion compositionally, structurally. And the reason why you see this distinct red-pink color is this large anion derived from the acidic phenolphthalein molecule has resonance. Did you learn about resonance in 2045? Large resonance systems often have the ability to interact with light from the visible region of the spectrum. What do you see when something interacts with so-called white light? What do you see? What do you call it? Color! How about that? Let's see if we can see some color with this stuff. Ha ha ha! Red pink? Lipstick red pink? Huh? What's this tell us? Remembering that I just reminded you that at pHs above 9, the acidic phenolphthalein molecule loses H+ and becomes this phenolphthalein anion, which exhibits considerable resonance stabilization, which interacts with white light and gives you a color. Red-pink. Does this tell you that when we dissolve calcium carbonate in water, that clearly something besides this happened? Or let me put it to you this way. When pH goes up in water solution, what does that mean? What does it mean? What does it mean? It means something is happening in the system which increases what? The what? Increases what? Hydroxide ion concentration, you betcha. Now then, because our calcium carbonate saturated solution on treatment with phenolphthalein indicator showed us this red-pink color, then we know that when we dissolve the calcium carbonate in preparing the saturated calcium carbonate solution, some of the dissolved calcium carbonate reacted with water to create hydroxide ions. That's why the system became basic. So if you know that one of the products is hydroxide ions, I charge you right now with the responsibility to write the other reaction which takes place when calcium carbonate is dissolved in water. The reaction which accounts for this development of red-pink color. Go on, try it right now on your paper. Let's go, quick! Remember, we've prompted you to recognize that this red-pink color development means this had to be created by this reaction. Did you learn to write this is the correct formula for hydroxide ion in 45 laboratory? Give me the textbook that writes OH minus. Out the door. I mean, damn it. Look at this. If I'm going to make hydroxide ion from a water molecule, I do so by breaking either HO bond heterolytically. How many ways can I break a covalent bond? How many ways can I break a covalent bond between different atoms? 3 ways, can I not? I can break the bond in half. In other words, the product fragments each have one unpaired electron in their valence structure. That's called homolytic bond rupture. Did you talk about that in 2045 lecture? Homolytic bond rupture. Did you talk about that in 2045 lecture? Well then, that's one more thing I got to get at 2045 lectures about, and say, what the hell are you doing? Or maybe I should say, what the hell are you not doing? You don't talk about bond rupture. What's going on in here? That's not your fault. You'll hear from me about this. Or I can break the bond this way. Now if I break the bond this way, this previously bonding electron pair winds up in the valence environment of the hydrogen atom fragment. That creates a hydride ion. But I'll bet you all know that if I break the OH bond heterolytically, which is the usual way an OH bond breaks, I break it like this. And the H leaves as H+. And the previously bonding electron pair winds up in the valence environment of the oxygen atom. And what does that do? It develops a formal charge of -1 on the oxygen atom. Right? HO minus? What the hell is this OH minus junk? That's stupid. I mean, it's stupid. It's flatly stupid. And everybody tells me, but that's tradition. I'll tell you what you can do with that tradition when it stands in the way of understanding. Well, I better reserve some of my language in here. I don't want the UFPD coming after me right away. Hydroxide ion. And after all, when we write formulas, is it not standard practice to write the symbol for the atom which is of lower electronegativity first? Come on now, what's this OH minus junk? That's a flat flunk. That's 1,000,000 points off. Get out of here with that stuff. All right, now back to this reaction equation. Because in this reaction equation, we are again starting out with the ionic compound, calcium carbonate, and we're looking at a reaction which involved the production of hydroxide ion. Clearly that means calcium carbonate had to react with water. Did that not mean that? This ain't got no hydrogen in it. So I'm going to make hydroxide ion. I got to react with water, because that's the only 2 things I put together, right? Calcium carbonate with water. So this had to be involved in the reaction. And not only did it have to be involved in the reaction, it had to be involved in the reaction like this. So something had to reach over to one of these water molecules and say, give me H+. What do you think that something is? You did this in 45 laboratory, put it to use. What reached over to this H water molecule and ripped H+ from it? Carbonate ion. Did you not learn in 45L, assignment 5, part 2, that carbonate ion is a very common weak base? You did some investigations about bronzyluric acid-base chemistry, which I had you do on purpose because that stuff is damn important and is damn difficult. In 45 lectures tell me, well, we don't want to talk about that because it's not part of the Constitution for 45. And I say, get the hell out of here. Your job is to teach chemistry. Better rewrite this Constitution. So, I got calcium ion, hydroxide ion, and what's the other ion produced? Remember, this was produced because carbonate ion behaved as a base, reached over to the water molecule, and ripped away H+. So what ion do you make when H+ lands on carbonate ion? You make What's its name? Hydrogen carbonate ion. Bicarb's all right, but hydrogen carbonate ion is a better ion. Now, next question. What's the correct formula for hydrogen carbonate ion? Because that's the other part of this puzzle. Write that on your paper right now. The correct formula for hydrogen carbonate ion. There's the textbook formula. You like this textbook formula? When carbonate ion reaches over to this water molecule and snags H+, what atomic component of carbonate ion snags this H+? A peripheral oxygen atom. The H+ snag winds up making a covalent bond to one of these peripheral oxygen atoms. Doesn't that make an OH bond? Because when I write formulas, I try to write them so that they keep with structure. Do you remember learning in 2045 that the most important property by far of any species is what? What is it? Structure! Structure! So I should write formulas that do the best job to keep with structure. That's the most important property of a species, by far. That's when you write down H2SO4 for the sulfuric acid molecule, and I demand that you write me a Lewis structure for that, and you start gluing hydrogen atoms to sulfur, because that's the implication of that stupid H2SO4 formula, you're wrong. And the textbooks are doing that all over the place for general chemistry. You think I'm going to use those books? You already know the answer to that, don't you? The hell with that trash. It doesn't belong in the chemistry classroom. You're never going to get mine. So, I write this because this shows me that the H+ strip from water glued onto an oxygen atom. Now, after you know this, I'll let you use this as a shorthand for this formula, but not until. So, beside this equilibrium, guess what? For saturated calcium carbonate solution, when water is dissolved, we can also write this equilibrium constant expression. And we will in fact do this when we get into chapter 18. So we're already building a bridge for what we're going to do in the future. But this is a legitimate equilibrium constant expression for this equilibrium system. So that's part and parcel of chapter 17. Now one more. System D. Consider the preparation of 1 molar acetic acid solution. Tell me, you got any acetic acid solution at home? Do you have any acetic acid solution at home?
Yeah.
What's its generic name?
Vinegar.
Vinegar! Use vinegar at home for making salad dressing? Other systems to flavor? Put a little vinegar and spritz it in a mist on mirrors and take some newspaper, wad it up. You clean that mirror, I mean so nicely. I mean it. Newspaper. Wad up newspaper, spray it with vinegar. You clean off that mirror, all the smudges, everything go away. Real pretty. That's what the pros do. The mirror people showed me that trick. I said, wonderful, it's chemistry, I love it. Now then, notice that this too is called an acid, like HCl hydrochloric acid, acetic acid, because each of these molecules has the chemical capacity to react with water and make hydronium ion. That is indeed the property of any species which establishes it to be a Bronsted-Lowry acid, which we'll be talking about in great deal in chapter 18, for which we're presently laying foundation. So, we see hydronium ion produced. That comes by stripping H+ from acetic acid. This, of course, is just an abbreviational formula for acetic acid. As acetate ion, the conjugate base of acetic acid is also produced. But there is a big difference between this reaction versus this reaction when the m sub I values for the solutions are each 1. So I'm going to go back to our flask. Now change the label to 1 molar HAC. Tell me. What do you know about the extent of this reaction? Hint, you did this in 45 laboratory assignment 4. What do you know about the extent of this reaction D when the label on the bottle says 1 capital MHAC? Very small. Anybody know how small, roughly? 0.4% is the extent. So for now, if you say less than 1%, that's good enough. Okay? So for extent, we'll say less than 1%. And when we get to chapter 18, we'll show you how to calculate the percent right on the nose. So comes the next question. Is there equilibrium in this system involving solute? And if so, what's the equilibrium constant expression? Is there equilibrium in this system involving solute? You're damn right. Hardly any of this disappeared. If less than 1% went away, that means more than 99% of it is still there after you made the solution. So then we can do this like we did for this system. And now we can write the equilibrium constant expression. Do it right now. The equilibrium constant expression for D there it is. How many wrote that? Reaction products, solute, but no water, because that's the solvent. That's treated as a pure liquid in this system. Question? Well, no, after I establish equilibrium, then I'm going to do this. Because originally the reaction equation I showed you is that which represents the chemistry that occurs when you dissolve the acetic acid in water to make the solution. And acetic acid by itself as a pure stuff is a liquid at normal lab conditions. All right? Now let's ask another question. I trust by now you've all recognized from your work in 2045 that this is just an abbreviational reference to acetic acid. What's the true formula for acetic acid? Write it on your paper right now. The true formula for acetic acid. Come on, let's go. All right, we'll give you this. Now then, another comment on the problems that we have in writing chemical formulas. Now, we also discussed this in 45 laboratory, but I don't know if you remember such. Question. In the acetic acid molecule, is there an oxygen-oxygen bond? Or for the acetic acid molecule, if you prefer. Is there an oxygen-to-oxygen covalent bond? No. Yes or no? No. But this formula implies such, doesn't it? Problem. Because if I'm going to do a better job, in representing the structure of the acetic acid molecule, its most important property, then I have to show you that one of these oxygens is doubly bonded to this carbon atom. There are no oxygen-oxygen bonds in this molecule. But how do I type this damn thing? There's the problem. There have been various attempts by organic textbook authors to figure out a way to do this, but they don't prove particularly satisfactory. So, are you recognizing the significance of our statement about structure being the most important property of species? And oftentimes you just can't represent structure by writing a chemical formula alone. Which is why, in many respects, the most important thing you were asked to learn about in 2045 was what? Writing what? Law structures. How about that? Are you all experts at writing Lewis structures? And if you're not now, you will be. Now then, look at the notes. You'll see various and sundry topics considered. One of which is what happens to an equilibrium system if we do something to disrupt the equilibrium? Now, once again, I take issue with textbooks because they invariably discuss this issue by saying, if I do something to disrupt an equilibrium, the equilibrium shifts. Have you heard that? Yeah. Equilibrium shifts? I have no use for that two-word phrase. There's no respectable equilibrium in the universe which will shift. It's the most stable state in which a system can exist. Why the hell should an equilibrium shift? Because what in fact happens when you do something to impact this equilibrium is to destroy the equilibrium. Well, how in the hell can something shift if it ain't there? Ain't that right, Le Chatelier? Huh? Did you read about Le Chatelier? Le Chatelier's principle? What does Le Chatelier's principle state? Le Chatelier's principle states, it's all in the notes, if we do something to disrupt an equilibrium system, if at all possible, a reaction will occur in the system after it's been disrupted. To do what? Re-establish equilibrium. It's the most stable state for the system, so I want to go back there. The natural thermodynamic drive is for that system to react and get back to equilibrium. So let's take a look at a couple of actions on this equilibrium system. Because this thing is like this. It's like a teeter-totter in balance when it's at equilibrium. How many of you played teeter-totter or seesaw? I played a lot of seesaw when I was a kid. I found out when I was down here and my seesaw partner was up here, going back and forth like this here. I jump up and and my partner did it to me. I said, oh, it's not so much fun. Tell me, if I take this system right here and add some more acetic acid, add some more pure acetic acid, at the very instant at which I added the additional acetic acid, what happens to my teeter-totter? The teeter-totter shifts, but at the instant at which I add the acetic acid, this condition is wrecked. The equilibrium is disrupted. And since I added a component of the system, the only thing that can happen to get me back to equilibrium, if such is possible, is this or this. Nothing else can happen. But Le Chatelier dictates that if at all possible, we're going to try to get back to equilibrium. So I ask, I added acetic acid, on adding the acetic acid, Which way does my teeter-totter shift? Does it now go like this here, or does it go this way? Which way? This way or this way? This way. Then I put more stuff here? Well, then this goes down, right? This side is now heavier than that side because I put more of this stuff in there. Okay? So it's like this. After adding this, my teeter-totter is no longer in balance. It now looks like this. So tell me, which of these reactions gets me back to equilibrium? Left to right or right to left? Left to right. Some more of this has to react, get together with water molecules, make more hydronium ions, more acetate ions, and then we can get back to equilibrium. That's how a system behaves. Now then, let's take a look, in concluding for today, at a somewhat more practical illustration of equilibrium and its establishment by looking at two cylinders. This is all in the notes. Cylinder A, cylinder B. A and B each have 200 milliliters of a water solution. This water solution in cylinder B contains some dissolved iodine. 200 milliliters H2O solution in A plus K plus and I minus. So in A, beside the water, I dissolve some potassium iodide. I'll tell you why in a moment. In B, in addition to my water and my potassium iodide, I also have I2. Now in the main, the I2 is in there as I3 minus, which shows you this color. Did you learn in 2045 laboratory that I2 is not very soluble in water? Is that unusual? Would you not well expect that a material like I2 is not going to be very soluble in material like water? Why not? Because of their great difference in electric natures, often referred to as polarity. Water is a highly electric molecule. Not only is it quite polar, it's a hydrogen bonder. But I2 is a simple homonuclear diatomic molecule, strictly nonpolar. So in order for this demonstration to be a lot more viewable on your part, the audience, I purposely laced the water solution with potassium iodide so that I can get this reaction to occur. This is a reaction which involves the formation of a coordinate covalent bond. Question: in 2045 lecture, did you hear anything at all about forming coordinate covalent bonds?
No.
Did you hear anything at all about Lewis acid, Lewis base chemistry?
No.
You did? Well, if you had something about Lewis acid, Lewis base chemistry, then you had to hear about forming coordinate covalent bonds, because that's what Lewis acid, Lewis base chemistry is. The formation of coordinate covalent bonds. But since, with those remarks, I'm seeing quite a few puzzled expressions, we'll stop here and pick it up from this point tomorrow.